Hello dear friends, welcome back to Math with Amala. Let's move to a new video which contains the part 9. Kindly go through the previous portions in order to get a continuation. Here we are dealing with the revisiting irrational numbers. So far we have concluded the exercise problems also including the Euclid's division algorithm. Now we are moving to the revisiting irrational numbers. Here let's take the irrational numbers. What are the irrational numbers that we have already studied in our previous class grade 9? They are root 2, root 3, root 5 and root p. You can generally say it like root p where p is a prime. P is a prime number. Let's take an irrational number. Yes. We know that rational means it should be of the form p by q where p and q are integers and q not equal to 0. But in irrational case, it is confirmed that p by q form is not possible there. So let's take an yes which is not satisfying the rational condition. Okay, so that is irrational number. This is how we will recall the irrational numbers. Let's move to theorem 1.2 which is of very important. Let p be a prime number. If p divides a square, then p divides a, where a is a positive integer. Actually, we are applying this theorem on different upcoming theorems in order to prove the theorems. So let's move to the proof of this theorem 1.2. Let's take the prime factorization of a. Since a is a positive integer, it should have a prime factorization p1 into p2 into etc. into pn, where p1, p2, pn are prime numbers. It is not necessary that they should be distinct. They can be same. The pi's can be same. P1, P2 can be same. P2, P3 can be same. Likewise, they can be similar. It's an example. Okay. Therefore, so I am using here three dots like this, and it means like therefore. It's a simple for therefore notation. Let's take a square. We have written what is a. Let's take a square. Then you will get p1, p2, etc. pn into p1, p2, etc. pn, which means we can multiply the p1s together. You will get p1 square, p2s together, p2 square, and pn's together, pn square. Okay, which means you are getting two numbers multiplied together and you will be resulting in its squaring. And in the theorem we are already given with p divides a square. Hence, by fundamental theorem of arithmetic, we can simply say it like p is one of the prime factors of a square. P divides a square. Let's take 6 equal to 3 into 2. Here you can say 2 divides 6. 2 is dividing 6 and the answer is 3. Likewise, you can say the prime factors will be dividing that number. Likewise, 3 divides 6. Okay. Next one, you can move to the uniqueness of this fundamental theorem of arithmetic. What that theorem gives you is the uniqueness. Let's take the prime factorization of a square. Then that a square includes p1, p2, etc. pn. So p is one of these prime factors. P is one of these prime factors or one among these prime factors. This symbol with three inverted dots like 2 and 1 like a inverted triangle denotes the since. The symbol denotes since. Since a is equal to p1, p2, etc. pn, p divides a. The reason is that the p is contained already in this p1, p2, etc. pn. So a is equal to p1, p2, etc. pn implies that p divides a. Hence we can say that. So we have found that if p divides a square, then p divides a automatically. By this theorem, you can prove root 2 is irrational. For this, we will be using the proof by contradiction method. In this method, you will be taking the first hypothesis as the assumption. Then by our procedures, we will prove that this assumption is wrong. Through some findings, we will be able to understand that this kind of reasons are not suitable here, which means the contradiction is arising at the assumption. Next is theorem 1.3, which is very important, and it states that root 2 is irrational. We have to prove that root 2 is irrational through the assumption and also through the contradiction method. Now let's see how to prove this with the contradiction method. Root 2 is irrational. In order to prove this, on the contrary, you can assume that root 2 is rational. Root 2 is rational. If a number is rational, it can be represented in the form a by b or p by q, where p and q are integer and q not equal to 0. So let's take root 2 as rational, and you can express it in the form p by q. Instead, we can take r and s, integers r and s, where root 2 is equal to r by s, where s not equal to 0. Here r and s are not having any common factors other than 1, because they are already in the prime format or they are co-prime. We can write root 2 is equal to a by b. A is equal to b into root 2. If we square on both sides, you will get a square is equal to b root 2 the whole square, which is equal to b square into 2. A square is equal to b square into 2. Simply you can write a square by 2 is equal to b square, which means 2 divides a square. Hence, by theorem 1.2, you can say that 2 divides a also. 2 divides a means a can be written like a by 2 is equal to c, where a is equal to 2 into c. This indicates that a can be written like the multiple of two numbers. A is equal to 2 into c. Now let us put this a is equal to 2c in a square is equal to 2b square, which is equal to 2c the whole square equal to 2b square, then 4 into c square is equal to 2 into b square. You can cut the 2's, and 2c square is equal to b square is the answer, which means 2 divides b square. Or you can simply say 2 divides b by the theorem 1.2. Therefore, we can say that a and b, both a and b, have 2 as a common factor, at least 2 as a common factor. Hence, this is a contradiction to our assumption. Hence, this contradicts the fact that a and b have no common factors other than 1. Okay, here we have found another common factor 2. So, this is a contradiction to our assumption. Hence, our assumption is wrong, which means root 2 is irrational. Thank you all for watching the video. Please be stay tuned for the next video.